Welcome to Module 3, Installing System Devices. This module covers core internal components you will install throughout your IT career, including power supplies, cooling, storage, memory, and CPUs. We will build hands-on skills essential for the job and for your certification exam. In this module, you will learn to install and configure power supplies, cooling systems, storage devices, system memory, and CPUs. These 4 areas will serve as the foundation for our upcoming lessons. Lesson 3.1 focuses on power supplies and cooling. This covers 2 key A plus 201 objectives, installing motherboards and CPUs, and installing or replacing power supplies. We will examine how power is delivered and how cooling keeps your system safe. By the end of this lesson, you will understand how to calculate total power requirements, why PSU efficiency is critical, the benefits of modular power supplies, the role of thermal paste and heat sinks, and how to maintain liquid cooling systems. This lesson covers a wide range of hardware, from basic power supply units and connectors to advanced cooling solutions like liquid cooling systems. We will explore each component to understand its specific function in your computer build. To maintain optimal performance and reliability, your system relies on effective power delivery and heat dissipation. This visual provides an overview of the cooling and power hardware we will be discussing throughout this session. The power supply unit is the heart of your system, converting wall power into the DC power your components require. When selecting a unit, remember that its physical dimensions must be compatible with your case and motherboard. Always verify your PSU's voltage requirements before plugging it in. While many modern power supplies are auto-switching, using a manual switch unit set to the incorrect voltage can cause permanent damage to your hardware. When planning a build, use a power supply calculator to ensure your PSU can handle the total wattage required by your components. This ensures your system remains stable under load. Wattage rating tells you how much power a PSU can provide. Remember that power is voltage multiplied by current. Beyond raw power, check for 80+ certification, which indicates the efficiency of the power conversion process. This chart highlights recommended wattage ratings based on your CPU and GPU pairing. Higher performance components typically demand higher wattage power supplies to maintain system stability. PSUs provide power through various connectors to supply 3.3, 5, and 12 volts to your components. These include standard SATA and Molex connectors, as well as specific connectors for CPUs and PCIe graphics cards. Familiarize yourself with these common power supply connectors. From the main 24-pin motherboard cable to specialized 6 or 8-pin connectors for your graphics card, each has a specific role in powering your system. While older systems used a 20-pin connector, modern motherboards standardly use a 24-pin P1 connector. If you are working with older hardware, you may need a 20 to 24-pin adapter cable to make the connection. Finally, consider modular power supplies. By using detachable cables, you can reduce internal clutter and significantly improve airflow, which helps keep your system running cooler and more reliably. Modular power supplies allow you to connect only the cables you need. This design choice reduces clutter, improves internal airflow, and makes cable management significantly cleaner for a more professional-looking build. On the connector side of a modular power supply, you can see individual sockets. This is where you plug in only the specific cables required for your components, rather than dealing with a fixed, bulky cable bundle. It is time for a hands-on activity. In pairs, you will identify the correct power supply for a system's specifications, install it, manage the cables for airflow, and select and install the appropriate CPU cooling system. Redundant power supplies are crucial for high-availability environments like data centers. By using 2 PSUs, the system can stay operational if one fails, preventing downtime and data loss. These units connect to a backplane and are hot swappable. This image shows a redundant power supply configuration. You can see 2 distinct modules that plug into a common backplane. This setup ensures that if a single module fails, the system continues to receive power from the secondary unit. Every electronic component generates heat due to electrical resistance. Effective cooling is essential, particularly for the CPU, to keep the hardware within its safe operating temperature range and prevent performance throttling or damage. A heatsink, typically made of copper or aluminum, uses fins to increase surface area for better heat dissipation. Thermal paste is then applied between the CPU and the heatsink to bridge microscopic air gaps and ensure efficient heat transfer. There are 2 main categories of cooling: passive and active. Passive cooling relies solely on the surface area of the heatsink to dissipate heat, while active cooling adds a fan to force air movement across those fins for much higher cooling efficiency. Fans are the primary tool for maintaining airflow. They are found in power supplies, at chassis exhaust points, and on CPU coolers. Remember to periodically clean these vents and fan blades with a soft brush or specialized vacuum to maintain performance. For high-performance workstations and gaming PCs, liquid cooling is often preferred. These systems use a pump to circulate water through a loop. They are generally quieter than air-cooled systems using many fans and consist of water blocks, tubing, a pump, and a radiator. Liquid cooling functions on principles similar to the cooling system in a motor vehicle, using fluid to carry heat away from critical components toward a radiator where it can be dissipated. Finally, the radiator and fans are critical components of a liquid cooling loop. The fans force air through the radiator fins, cooling the heated liquid as it passes through, so it can return to the CPU at a much lower temperature. Welcome to this video on storage devices, which maps to CompTIA A plus Exam Objective 3.4. We'll explore various storage technologies, their performance, and their ideal use cases. In this video, we will examine the differences between SSDs and HDDs, look at RAID configurations, and explain how SD card ratings affect performance and capacity. We have quite a bit to cover. We'll start with an overview of mass storage technologies, and then dive deep into various RAID levels, including RAID 0, 1, 5, 10, and 6. Mass storage devices are non-volatile, meaning they retain data without power. They use magnetic, optical, or solid-state technology. When selecting one, consider reliability, performance, and your intended use. Solid-state drives, or SSDs, use flash memory and offer superior read performance compared to HDDs. They are less prone to mechanical failure because they contain no moving parts. For everyday use, SSDs generally outperform hard disk drives. However, HDDs are often preferred for bulk storage due to their lower cost per gigabyte and specific archival advantages. This video shows the difference between high-performance NVMe M2 SSDs and standard SATA 2.5-inch drives. Both are cooler, quieter, and more efficient than traditional mechanical drives. Hard disk drives store data on magnetic platters. Performance is largely dictated by the drive's spindle speed, measured in revolutions per minute. When you look inside a traditional HDD, you'll see the complex mechanical assembly of platters and read/write heads. Contrast this with SSDs, which use NAND flash memory chips. This view illustrates the physical layout of an HDD, including the disk sector, tracks, and clusters, showing exactly where data is physically stored and accessed. RAID, or Redundant Array of Independent Disks, allows us to mitigate data loss risk by distributing data across multiple disks, balancing performance and fault tolerance. Choosing a RAID level depends on your specific needs. RAID 0 focuses on performance via striping, while RAID 1 provides redundancy through mirroring. In RAID 0, data is split into blocks and striped across drives. This maximizes speed but provides no redundancy, so one drive failure results in total data loss. RAID 1 uses mirroring. Each drive contains an identical copy of the data. If one drive fails, the data remains safely accessible on the secondary drive. Finally, RAID 5 uses distributed parity for fault tolerance, allowing recovery after a single disk failure. RAID 6 adds a second layer of parity, surviving 2 disk failures. This video illustrates how parity blocks are laid out across the array in RAID 5 and RAID 6. Notice how RAID 6 uses twice the parity data to provide that extra layer of fault tolerance. RAID 10, often called a stripe of mirrors, combines RAID 0 and RAID 1. Data is striped across mirrored pairs, offering both high performance and robust redundancy. In this layout, you can see the striping mechanism in action across pairs of disks, where each pair serves as a mirror for the other, protecting your data. It is time for a simulation activity. Use the provided RAID simulator tool to configure various RAID levels, record their performance and fault tolerance characteristics, and discuss which is best for specific scenarios. Removable and external storage drives allow you to move data between computers without opening the case. Drive enclosures enable you to turn standard internal drives into convenient external storage. Here, we see a variety of removable storage options, including enclosures, USB flash drives, and memory cards, highlighting the different form factors available for portable data. Optical drives use lasers to read data from disks. These come in various formats, such as recordable and rewritable media, each with different capacities and transfer rates. Finally, comparing CD, DVD, and Blu-ray discs reveals how physical differences in the media directly affect the storage capacity of each format. Welcome to our video on system memory. This lesson covers A+2201 Objective 3.3, where we'll compare and contrast key RAM characteristics, including how system RAM and virtual memory work together, various RAM types, modules, multi-channel configurations, and ECC RAM. In this video, we'll explore the essential role of system RAM and how virtual memory provides a safety net when RAM is full. We'll also examine the differences between DDR3, DDR4, and DDR5, and why matching the correct RAM module to your motherboard is crucial. We will break down memory configurations, explaining how dual, triple, and quadruple channel setups can boost performance. Finally, we'll define Error Correction Code, or ECC RAM, and look at how it helps maintain system stability by preventing data corruption. System RAM is significantly faster than storage devices like SSDs or HDDs, but it is volatile, meaning it requires power to retain data. The CPU manages memory through two specific pathways: the data pathway, which handles the information transferred per clock cycle, and the address pathway, which identifies memory locations. Understanding RAM types starts with DRAM, or dynamic RAM, which stores bits and capacitors. Synchronous DRAM, or SDRAM, improve this by syncing with the system clock. Today we primarily use double data rate SDRAM, which doubles bandwidth by transferring data on both the rising and falling edges of the clock signal. Let's examine the different physical forms of memory modules. We have standards like DDR4 and the faster, more efficient DDR5. We also have compact forms like SODIMM, designed for laptops, and specialized modules like ECC RAM for mission-critical workstations and servers. Random access memory provides fast, temporary storage for running applications. Because it is volatile, all data is lost when the power is turned off. Choosing the right type, like DDR3, 4, or 5, is essential for compatibility and optimal performance. Here you can see a SODIMM module installed in a laptop. The notch on the module is a critical feature, as it ensures correct alignment and prevents you from installing a module into a slot that isn't electrically compatible with that specific memory generation. This video shows the physical differences between desktop DIMM slots and older SIMM slots. The physical design of these modules has evolved over time, using specific notches and pin counts to ensure that only the correct generation of RAM is installed in a system. To summarize the evolution, dynamic RAM is the oldest, simplest form. Synchronous DRAM, introduced in 1993, brought predictability by syncing with the clock. Since 1996, DDR-SDRAM has been the standard, continuously improving speed and power efficiency across generations like DDR4 and DDR5. Memory modules are simply printed circuit boards that group RAM chips into a single, manageable unit. Desktops utilize the larger DIMM format, while laptops and other space-constrained devices rely on the compact SODIMM or small outline DIMM standard. This visual demonstrates the vast variety of memory modules that have existed over the years, from early 30-pin SIMMs to modern high-speed DDR4 and DDR5 modules. The size and pin layout are specific to the generation and form factor of the host device. Dynamic RAM, or DRAM, is the foundation of modern memory. It uses capacitor and transistor cells to store data, which necessitates frequent refreshing to prevent data loss. While it has been largely superseded in high-performance contexts by newer, faster technologies, it remains a fundamental concept. Synchronous DRAM, or SDRAM, was the dominant standard for PCs in the late 90s and early 2000s. By synchronizing with the system clock, it allowed memory operations to align perfectly with CPU timing, though it is now considered legacy technology replaced by faster DDR standards. Finally, we have modern double data rate SDRAM. By transferring data on both the rising and falling edges of the clock signal, it effectively doubles bandwidth. With multiple generations available today, it remains the gold standard for desktops, laptops, and servers alike. Now let's look at the physical evolution of memory modules from DDR1 through DDR5. You'll notice how the notch position changes with each generation, which is a key safety feature that prevents you from accidentally installing a module into an electrically incompatible slot. Next, we explore multi-channel system memory. We'll cover how single, dual, triple, and quadruple channel memory work, how to properly configure slot arrangements for maximum performance, and how features like flex mode handle mismatched modules. Single-channel memory uses a single 64-bit bus, which is standard but limited in speed. Dual-channel memory doubles this with two 64-bit pathways, totaling 128 bits. Triple and quad-channel configurations add further parallel buses, providing even higher bandwidth for high-performance servers and desktops. When installing memory, ensure you use the correct slot arrangement, often color-coded on motherboards, to enable multi-channel mode. Your BIOS, or UEFI, should auto-detect this setup. If you use mismatched modules, your system may use flex mode, running part of the memory in dual channel and the rest in single channel. Finally, we have ECC RAM, or Error Correction Code memory. It is designed for high-reliability environments to prevent data corruption and unexpected system crashes. Always verify if your motherboard and CPU support ECC before installation. To see the difference, notice the extra memory chip on this ECC module compared to standard RAM. That chip is specifically responsible for storing the error correction data that keeps critical systems running reliably. Lesson 3.4: CPUs. This lesson maps to A+2201-201 Objective 3.5, installing and configuring motherboards, CPUs, and add-on cards. We'll cover CPU architecture, features, socket types, and how to match a CPU to a compatible motherboard. Here's what this lesson covers: CPU architecture, including x86, x64, and ARM, CPU features, CPU socket types, and CPU to motherboard compatibility. When a software program runs, its instructions get assembled using the CPU's instruction set and loaded into memory. The CPU then performs 4 basic operations on each instruction in order: fetch, decode, execute, and write back. That 4-step cycle is the foundation of everything a CPU does. x86 architecture defines how a 32-bit CPU processes instructions and data. It's also called IA32, and without extensions, it's limited to 4 GB of addressable memory. 2 major design approaches shape CPU architecture generally: reduced instruction set computing, or RISC, which uses a small, simple instruction set for speed and efficiency, and complex instruction set computing, or CISC, which uses a larger instruction set to handle complex operations directly. x86 CPUs rely on a few key components: the arithmetic logic unit, or ALU, which performs math and logic operations, the control unit, which directs the flow of instructions and data, performance features like cache, clock speed, and core count, and hyperthreading, which lets one physical core handle multiple threads for better multitasking. x64 architecture handles 64-bit instructions and data paths, letting a CPU address vastly larger amounts of memory, theoretically exabytes, practically terabytes in real systems. It maintains backward compatibility, running both 32-bit and 64-bit software, though newer operating systems are dropping 32-bit support. Compared to x86, x64 supports more registers, better performance, and stronger security features. Here's x86 and x64 architecture compared side by side. The difference in addressable memory and register count is what ultimately separates what each can do. ARM CPU architecture uses a RISC-based design, a small, efficient instruction set that's fast and power efficient. ARM chips are typically built as a system-on-chip, or society, combining the CPU, GPU, memory controllers, and I/O onto a single chip. You'll find ARM in smartphones, tablets, IoT devices, and increasingly laptops too, like Apple's M1 and M2 chips. Software has to be compiled specifically for the ARM instruction set, and physically, ARM chips are typically soldered directly to the motherboard, compact, lightweight, and low power with excellent heat management. Here's where each CPU architecture actually shows up in practice. x86, 32-bit, mostly lives on in legacy PCs and laptops from before the early 2010s. x64, 64-bit, is the standard in modern desktops, laptops, and servers. Everything from engineering workstations to gaming PCs runs on it. And ARM, RISC-based, dominates mobile devices, IoT and embedded systems, the Raspberry Pi, and is increasingly showing up in laptops and even cloud servers, like Apple's M-Series Macs and AWS Graviton instances. 3 CPU features worth knowing. Simultaneous multithreading lets multiple instruction streams run on a single core at once, so each physical core appears to the operating system as 2 logical cores. Intel calls its version hyperthreading. Symmetric multiprocessing uses 2 or more physical CPUs sharing memory and tasks in one system, common in enterprise servers. And chip-level multiprocessing places multiple cores on a single CPU chip, which is what gives you quad-core, octa-core, and similar modern CPUs. Here's how L1, L2, and L3 cache are laid out relative to the CPU cores. Notice how each level gets progressively larger and slower as you move further from the core, trading speed for capacity. Here's a land grid array socket using a zero insertion force, or ZIF mechanism. Notice the small pins in the socket itself rather than on the CPU, which is the defining feature of an LGA design. CPU sockets come in 2 main families. Pin grid array, or PGA, puts the pins on the CPU itself. That's AMD's approach. Land grid array, or LGA, puts the pins in the socket instead, with flat contacts on the CPU. That's Intel's approach. Both use a zero insertion force mechanism, so the CPU drops into place without any pressure needed. Installing a CPU comes down to 4 steps. Insert the CPU into the socket, aligned correctly using the notches or corner markings. Apply a small amount of thermal paste, pea-sized, or a thin line down the center of the CPU's heat spreader. Mount the heatsink firmly over the CPU, using push pins, screws, or retention clips depending on the cooler type. And connect the fan cable to the CPU_fan header on the motherboard so the system can actually manage cooling. Here's what that installation actually looks like in practice. The CPU seated in its socket, thermal paste applied, and the heatsink mounted and secured on top. Selecting a compatible CPU means checking 3 things. The socket type, like LGA1200 or AM5, has to match the motherboard. Chipset support matters too, since not every CPU works on every board even with a matching socket. and you may need a BIOS or UEFI update for a newer CPU and an older board. When comparing CPUs, look at core count and threads, clock speed and boost technology, cache size and TDP, or thermal design power. The right choice comes down to use case, budget versus performance, upgradability, and compatibility with your RAM and cooling. To wrap up Module 3, IT specialists need to select components that can withstand the temperature and humidity conditions they'll actually operate in. Choosing and installing the right storage devices keeps data reliable for whatever the use case demands. Understanding RAM characteristics ensures system memory gets configured and installed correctly. And installing and configuring motherboards, CPUs, and add-on cards correctly is what delivers both performance and long-term reliability.